This is the second section in the momentum and impulse chapter, and this is the conservation of momentum, section 1.2. Now you'll see a couple of diagrams here. So the first one shows two particles colliding with each other, and at the point of collision they give each other this equal and opposite impulse. So this impulse here, which is pointing to the left, let's label these particles A and B. So let's call this A and this one B. So this impulse represents the impulse exerted on A by B, so given to A from B, so B sort of hits it, and this is that arrow that represents that. So the impulse exerted on particle A by particle B, and this impulse, this arrow, represents the impulse exerted on B by A. So this represents like the hit, the punch, like that A gives to B. Now because these are equal and opposite, yeah, these will always be equal and opposite, then we can use that to give us a formula which is what we call the conservation of linear momentum. Conservation of linear momentum. Now what that basically means is the total momentum before the collision is equal to the total momentum after the collision, because these impulses here. Yeah, now later on you'll see actually that if we start to factor in other things to do with loss of energy and something where you're looking at the coefficient of restitution, that comes later on, you'll see that actually there is some momentum lost. But for now we're just going to say the total momentum before equals the total momentum afterwards. It's written here, yeah, and then this side over here represents the total momentum before, so the momentum of particle 1 and particle 2 equals the momentum of particle 1 and particle 2 afterwards. And I think this is a YouTube clip here to do with snooker balls and things like that. No, actually it's to do with different balls bouncing on each other, some physics scale video that you can watch where if you have a big ball and a small ball on top of it and you bounce them, the small ball goes way up in the air. Have a watch of it anyway and see. A particle P of mass 2 kg is moving with speed 3 meters per second on a smooth horizontal plane. Particle Q of mass 3 meters per second is at rest on the plane. Particle P collides with particle Q, and after the collision Q moves off with speed 7/3 meters per second. Right, so before we do anything, we're going to draw a diagram of what's going on. So this is P, which is 2 kg. This is Q, which is 3 kg. Now before the collision, P is well, it doesn't say it's moving towards P, but Q, but it must be if they collide. And Q is at rest, so we'll put 0 meters per second here. After the collision, so let me just write down before at the top. We normally do this way, and then after at the bottom. So afterwards, we see that Q moves off with speed 7/3. Now it must move off in this direction. Yeah, sort of common sense will tell you, well, if it's been hit by something and it's at rest, that's the direction it moves in. But we do not know the direction that P moves in, so we're going to have to assume a direction. Now I'm going to assume it's going to bounce back that way. If I am wrong, then when I do my working, I will get a negative, which is going to tell me it's moving in the other direction. So we need to look at the sign of our answer, which also means we need to decide which direction we're taking as positive. So let's call this the velocity of P. And in my working, I will take this direction as positive. It doesn't really matter. You may decide to take the other direction as positive, but I'm just taking that direction as positive. So by the conservation of linear momentum, yeah, so we can write it like that, we know that the total momentum before is equal to the total momentum afterwards. So the momentum before is the mass times the velocity of p before the collision, and the mass times the velocity of q before the collision, equals the mass times the velocity of p after the collision. Now, because p is, I've got that arrow going that way, so if I put arrows on, that's going that way, that's going that way. I've taken VP as that way, so I need to take it as a negative in my working, plus the velocity of Q, so 3 times 7/3. So that's a positive because we're taking it that way. So let's work it out. So we've got 6 over here, nice and easy. Then we've got minus 2 VP plus 7. So if I take 7 from both sides, I'll have -1 equals -2 VP. So that means that VP equals -1 divided by -2, which is 1/2 meters per second. Now, because this comes out as a positive here, it means that I've got my direction here correct. That's the way that it actually moves. If I got -1/2 here, it means it's moving to the right. So the speed and the direction, so that's the speed. So I could say something like to the left, or I could say something that it reverses direction. Yeah, because P reverses the direction it was going in. Something like that, but don't forget to mention the direction it's going in. So that's part A. And then part B, the magnitude of the impulse received by P in the collision, right? So if I put the impulses on like this, these red arrows, so this one is the impulse received by P. Let's say it the other way. This is the impulse exerted on P by Q. This is the impulse exerted on Q by P. Yeah, so that arrow represents what punch or push this has given this one, whereas this arrow represents the punch or push that this one, P, has given this one. Now, it doesn't matter which one we work out. I can use the working here to work out the impulse, or here. Now, my suggestion would be that you use this one, because if you work out VP and it's wrong, then you're going to get your impulse wrong. Whereas here, I know U and V already, yeah? And that way, I can't really make a mistake because I'm just going on the information I've been given. Whereas I work out VP, let's say I get the wrong answer, then when I work out the impulse, I'm going to get it wrong. So always try and use the information that's given to work out an answer. Sometimes you've got no choice, you have to use your own answer. Right, so impulse is change in momentum, so mv minus nu. I want me to take a direction as positive. Now, since I'm using this one here and the impulse is pointing that way, let's take that direction as positive. So I'll get a positive answer for my impulse. So mass 3 times by the velocity afterwards, which is 7/3, minus the mass times the velocity before. So I get an impulse of 7 Newton seconds. So I'll just underline that and underline that bit there. Two particles A and B of masses 2 kg and 4 kg are moving towards each other in opposite directions. So let's start to draw this before I as I'm doing it. So A and B, 2 kg and 4 kg. It says they're moving toward each other. Okay, like that. So they're both moving. The particles collide. Before the collisions, the speed of A and B are 3 and 2. So I'm just going to write the numbers 3 and 2. I'm not going to put meters per second. After the collision, the motion of A is reversed. So it means it goes that way, reversed, and its speed is 2. Find the speed and direction of B after the collision. Now, because we don't know which direction it's moving in, we're going to have to make an assumption. I'm going to assume that B also changes direction and goes this way. So this is going to be the velocity of B after the collision. Again, if it's the other direction, I'll get a negative in my working. And in part A, I'm going to take to the right here as positive. So we're going to use the conservation of linear momentum. So the momentum before is going to be 2 times 3 plus 4 times negative 2. Yeah, because look at the direction the velocity is in, and look what direction I've taken as positive. That will equal the momentum afterwards. So that's going to be 2 times negative 2. Again, look at the direction, plus 4 VB. Right, let's work that out. So we've got 6 minus 8 equals negative 4 plus 4 VB. So 6 minus 4, 8 is negative 2, negative 2, then I'm going to be adding 4 is going to be 2, so I've got 4 VB equals 2, VB equals 2 divided by 4, which is a half. So the velocity of B after the collision is a half, and the direction, I could say that it reverses direction, or it's to the right, so I'll put to the right, or you could write down B reverses direction. So either one of those give you information about which way that B is going. And in part B, the magnitude of the impulse given by A to B in a collision. Now remember, I could work out the magnitude given by B to A. It doesn't matter because they're equal and opposite, so either one of those impulses. So if I draw my impulse on a diagram, so this is the impulse of given by A to B, and this impulse over here, this is the impulse given by B to A, and it doesn't matter which one I work out because they're equal and opposite. Again, I'm going to try avoid using this, because if this is wrong, then I'm going to get my impulse wrong. I've got all this information here, so let's use that. So impulse equals this change in momentum. So I'm going to be working out the impulse given by B to A. So my impulse is equal to 2 times. Now again, I need to decide on a positive direction. Since my impulse is pointing that way, I'm going to take that direction as positive, so to the left, same direction as my impulse, makes sense. So 2 times, now the velocity afterwards is going to be 2, because it's the same direction as I'm taking positive, minus then 2 times by, now the velocity is pointing the other direction, so it's got to be negative 3. So that will give me 4 plus 6. So I'll get an impulse of 10 Newton seconds. Two particles P and Q of masses 8 kg and 2 kg, like this. So PQ, 8 kg, 2 kg are connected by light inextensible string. They're both at rest, okay. And it says the string is slack, like this. Particle P is projected away from Q with speed 4 meters per second. Okay, find the common speed of the particles after the string goes taut. Now, this is slightly different to before. Now, when the string goes taut, okay, so basically what you've got is a particle, a piece of string, a particle like that. Yeah, because they're traveling at in the same direction, at the same speed, we can clump them together and treat it as a single particle. Okay, so after the collision, we can treat A and B as one particle, because they're going, after the collision, they're going to be traveling at the same speed in the same direction. So we could draw another diagram actually to show what happens once the string is taut, like this. Yeah, so we got P and Q. So when the string goes taut, this happens. This is traveling at 4. This would be traveling at 0. Yeah, so this, the moment the string goes completely straight, P will be traveling at 4, Q's not moving, and then what's going to happen is they're both going to go off in this direction. And what we need to work out is what is this common speed afterwards, and that's, well, the speed of both of them is going to be the same. But what we can do is we can put their masses together and treat it as one particle, and we can do that when two particles are traveling sort of together at the same speed and they're connected by maybe string, rope, a uniform rod, tow bar, all that type of thing. Right, so let's work through this then. So part A, so before our collision, so conservation of linear momentum. So the total momentum before, I'm going to take this direction as positive because this is the direction they're moving afterwards. Seems to make sense. So the momentum of P before the collision is 4 times 8. The momentum of Q before the collision is 2 times 0. Sorry, that should be a plus sign. 2 times 0 equals, so the momentum of after the collision, we now put them together and treat them as a single object. Later we'll talk about the word coalesce, as if like they've joined together and become one. So now we just use the total mass, which is 10, times by their common velocity, which I'll call the velocity of PQ. Okay, so this 10 here is the total mass. So you treat them as one because of the reasons we've said before. Right, so what does that give us? That gives us 10 times the velocity, the common velocity of P and Q, equals 32. So this common velocity of P and Q is equal to 3.2 meters per second. In part B now, it talks about the magnitude of the impulse transmitted through the string when it goes taut. Now you can actually think of this impulse like the tension. Yeah, that's like the impulse, this sort of pull, and I will draw it on my diagram like this. So before, when they collided, the impulses were pointing in opposite directions. In this one, can you see the impulses are pointing towards each other? Because you could think of, well, at the moment the string goes taut, this particle P gets a pull back to the right by the string, whereas particle Q gets this pull to the left by the same piece of string. So our impulse is going to look slightly different on our diagrams. Now I can use either P or Q to work out the impulse. I'm going to use P. So if I just draw my diagram for P like this, so let's put down that this is P here. It was 4 that way, and after it's a speed of 3.2, so P is 8 kg, and my impulse is going this way. That's because the impulse is basically being transmitted through the string. As I said, it's a bit, you can think of it like a tension in a way. So let's take this direction as positive, since the impulse is going that way. Impulse is changing momentum, mv minus mu. So that's going to be 8 times by 3.2, negative 3.2 because of the direction, I mustn't forget that. So 8 times by negative 3.2 minus 8 times, now that is also going in the other direction, so that's going to be negative 4. So 8 times by negative 3.2 is negative 25.6, so minus 25.6. And then 8 times by negative 4 is negative 32, but we're subtracting that, so it becomes plus. So negative 25.6 plus 32 gives us 6.4 Newton seconds as the impulse transmitted through the string, or transmitted through the string. Right, so we've got two particles, A and B. A and B. A is 2 kg, B is 4 kg. We're told that they're moving towards each other in the opposite direction. Now that's important. Things can move towards each other in the same direction. So for example, if A was moving faster than B, then A would be moving towards B, but they'd be travelling in the same direction. So that's important that that's mentioned, that they're moving in the opposite direction. The speeds before the collision are 3 and 2. So I could write before here. And then after the collision, well, we're not told that, we need to work out, but we are told that the impulse due to the collision is 7 Newton seconds. So let's put that on. So these are the impulses that they give each other, equal and opposite. Now after the collision, I'm going to assume that the directions are reversed, that they bounce, hit each other and bounce away from each other. So okay, now if I'm wrong, it doesn't matter, I'll get a negative in my answer. So part A. So for part A, I'm going to be using this part of the diagram to get my impulse momentum principle. So I equals mv minus mu, and I'm going to take to the left as positive, so that'll give me 7 equals 2va minus 2 times negative 3. Look at the direction of the velocity before, so it's going that way, that's why it was a negative. So 7 equals 2va plus 6. Take away 6 from both sides, so 2va equals 1. Va equals a half, or 0.5 meters per second. So we know that it's going to be going in that direction. So I suppose you could put that in your answer. You could say instead that it's going to the left, So both of these tell you about the direction. Or you could say that the direction of A is reversed by the collision. That also tells you the direction. So direction of A reversed by collision. So we must include the direction as part of our answer, because we need to give a velocity as an answer, not just a speed. So I'll highlight that there. We're now going to do the same type of thing for part B. So in part B, we're going to be using this to do our working. So part B, velocity of B after the collision. So again, impulse momentum principle, and I'm going to take to the right as positive. So that means my impulse is 7, positive. The mass is 4. The velocity is VB after the collision minus 4 times. Now before the collision, it's doing 2, but in the other direction. So that will give me 7 equals 4 VB plus 8. So we'll take 8 away from both sides. We get 4 VB equals -1, which gives us VB equals -1/4 or -0.25. Now what does that tell us? Now since I assumed it was going that way and I got a negative, actually tells me that VB is going that way. So again, I can do the arrow, or I can say that it's to the left. Now since I've actually worked out that VB is travelling in this direction, in that purple arrow, it means that the direction of VB is not reversed, the direction of VB is maintained. So instead I could write down the direction of VB is maintained, or does not change, something like that. So you should now be able to do exercise 1B on pages 7 to 8. So just a reminder, this conservation of linear momentum is going to give us the total momentum before. So masses M1 and M2 with their velocities before the collision. Sorry, that should be U there. M2U2 is going to equal the total momentum after the collision. So these are the momentums after the collision.